Hello! In this video, we are going to prove the following lemma. Let A be a set and consider the identity relation on A. The following are true. One is that for all objects x and y, if x comma y is an element of the identity relation on A, then x is equal to I, which is an element of A. Second, for all elements x and A, x comma x is an element of the identity relation on A. Now, this proof is based off of principles in Daniel Velleman's book, How to Prove It. And the way that he defines the identity relation on A is as follows. It's the set of all ordered pairs x comma y in A times A such that x is equal to y. So this is what we're going to be working off of. Okay, but now let's prove the lemma. Let's start by proving 1. And notice in statement 1, we're trying to prove a statement about any two objects. So give me any two objects. I'll call them x and y. And our goal with x and y is to prove if this is true, then this is true. So let's suppose that this is true. What does it mean for x comma y to be an element of the identity relation on A? Well, it means that x comma y is an element of A times A, and x is equal to y. And what does it mean for an ordered pair to be an element of a Cartesian product? Well, it means that the first coordinate is an element of the first set, and the second coordinate is an element of the second set. So in particular, we can say that y is an element of A. So putting this together, we have that x is equal to y, and y is an element of A. And really, this is shorthand for saying both this and this are true. And this is exactly what we wanted to prove, so this proves 1. Now we're going to prove 2. And to prove 2, we're trying to prove a statement about every element in A. So give me an arbitrary element in A. I'll call it x. Our goal with x is to prove that x comma x is an element of the identity relation on A. Now, since x is an element of A, it follows that x comma x is an element of A times A. And if we decide to be extremely careful in how we can justify that, well, if we recall, the following fact is true. Given A, B, capital A, and capital B, we have that A comma B is an element of A times B, if and only if A is an element of A and B is an element of B. So applying this to our proof, if we take A and B to be x and x, we take capital A and capital B to be capital A and capital A, what we get here is that x comma x is an element of A times A, if and only if x is an element of A and x is an element of A. So this is true. And since we know that x is an element of A, it follows that both x is an element of A and x is an element of A. And since this statement is true and this is true, it follows that this is true. So x comma x is an element of A times A. But now, we can observe that x comma x is an element of the identity relation on A, because if we take x comma y to be x comma x, well, yeah, x comma x is an element of A times A, that's what we have right here, and x is equal to x. So yeah, x comma x satisfies all the requirements to be an element of the identity relation on A. So, putting this together, we start with an arbitrary element in x and A, and deduce that x comma x is an element of the identity relation A. And that's exactly what we have proven here. So, this completes the proof of 2. So, we've proven both 1 and 2. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, these two facts we will often use when dealing with the identity relation. So that's the reason why we've done this. So yeah, that's pretty much it for this video.